Okay. Again, feel free to interrupt and ask any questions throughout this because I want to make sure that you understand some things while we're going along with this. But I decided to start the exam with an empirical formula problem that involved organic. And so my theme for the first one was going to be organic chemistry themed, but not necessarily all topic 10. And so the first thing we had to do was we had to calculate the empirical formula of the substance using combustion products. And so the idea was that you had some biochemical that has carbon, hydrogen, and oxygen combusting into CO2 and H2O. And this is 12.915 grams. This is 18.942 grams, and this is 7.749 grams. Okay. And again, according to conservation of mass, what we know is that this amount of carbon, whatever mass of carbon that was produced in this, is the amount of carbon that's in this compound. And the amount of H that's in here is the amount of H in this compound as well. And so your goal there is to try to figure out those elements so that you can deduce the empirical formula, because what you need to have is the grams of carbon, the grams of hydrogen, and the grams of oxygen to be able to do this problem. So how do we do that? Well, we look at our percent composition, because every sample of CO2 has 12.01 grams of C for every 44.01 grams of CO2. So that percentage is always true in CO2. So if we multiply that by 18.942, we can calculate the mass of carbon that's contained in 18.942 grams. So 12.01 divided by 44.01 times 18.942 gets us 5.169 grams of carbon. We do the same thing with hydrogen, but you have to be careful because hydrogen is 2.02 because there's two hydrogens in water. Yeah, 18.02. So we multiply that by 7.749. Okay. And we get 0.86 grams of hydrogen. Okay. Now, how are we going to find the amount of oxygen? Just subtract, exactly. Because oxygen is the remaining element in this entire mass of 12.915. So we find that it's 6.8774 grams of oxygen. Okay. So that would probably be part A, to be honest with you. Like the way I wrote it, it just says determine the empirical formula. Probably what would happen on the real IB exam, they'd probably be A, calculate the mass of each element present, carbon, hydrogen, oxygen. Then part B would be using values from A, calculate the empirical formula. And so now that we have these masses, we can convert to empirical formula. And to compare different elements, we need to go to what unit?
Mole.
Every time you have
You need to go to mole.
Yes, thank you. You have to convert to moles because moles are the only type of unit you can compare different substances to each other. So you need to convert each of these. Yes. Correct. Yes. You can do it this way as well if y'all do proportion method. But again, this is one of those examples of not having to memorize whether you multiply or divide, because if you set a proportion or you set up your factor label, that setup determines whether you multiply or divide or not. Stop wasting time trying to memorize, oh, to get to mass, I multiply by moles, or when I get to moles, I have to divide by mass. Just set up the work and it will answer the question for you. And so that's one less thing you need to try to memorize, and one less thing that you'll make a mistake on by dividing or memorizing the wrong way, because on the test, you don't get my look of judgment when you say it wrong. Okay, unfortunately. Huh? Yeah, or why. So you have to be able to trust yourself to be able to do this. Okay. moles, moles, and moles. And now once you get all the moles, you want to convert to the simplest ratio. And so you divide by the smallest number of moles. And you end up getting C1H2O1. Okay. So your empirical formula is CH2O. Okay. That could be a real formula. It might not be a real formula. Empirical formulas are not required to make sense. They're just required to have the elements in a ratio with each other. Like sometimes you'll get an empirical formula of CH2, and that's not a real compound. There's no way carbon can bond enough times to two H's to make a formula. So it's okay. The empirical formula doesn't necessarily have to make sense. Okay. Questions about that process here? Make sure I'm recording. Okay. Now, so what is the IB going to do? The IB is going to incorporate analytical chemistry into this as well to make sure that you understand how to read the different spectra. Okay. So what they ask here is, here's the mass spectrum for the biochemical substance below. Determine the molecular formula of the compound. Okay. What about this mass spectra is going to tell you information you need to know for the molecular formula? Well, okay, that is some information you need on this, but to calculate the molecular formula alone, what information do you take from this, Alexandra? With the highest peak. This peak right here. Remember, this is called the molecular ion peak. This represents the entire molecule as a positive charged ion. I don't know if there's an extra blank test there, Ethnon, if you need it. Okay. So what that tells you is the mass is 60, okay? So that peak, but yes, Marina is right. This also tells you other fragments and things like that in the structure that can help you deduce that. In this case, we're not using that information, but they might ask you about that, like what represents the 43 peak or the 45 peak or the 15 peak. But so why that's important is the molecular formula weighs 60 grams, okay? To find the molecular formula with the empirical formula, you divide by the mass of this, which ends up being 30 grams, because 12 plus 2 plus 16 is 30, which means that your molecular formula is 2 times as big as your empirical formula. Okay, yes, Matthew. It doesn't matter. The intensity of the peaks does not matter in mass spectrum. It is just the presence of peaks. Is different fragments of the same, yes. So, yeah, like what mass, like, yeah, you'll be looking at the mass of those fragments and label in data booklet when necessary, yeah. And so, yeah, we're not worried about intensity here. That's something if you continue in analytical chemistry in college that they'll talk about, like which one's the most the predominant fragment and things like that, but we're not going to talk about that. Okay. Now, letter C. Using this, yes, sorry, Cass. Yes, the highest peak is a molecular ion peak, which represents the molecular formula mass. So essentially what this peak represents is C2H4O2 positive. Remember, if they ask you for what the formula of the structure that represents that peak, you need to put a positive charge. If it's a fragment lost, you don't need to put a positive. But if it's a fragment that's showing up on there, they're all positive ions. So put a positive next to it. So, no, not in this test, but in other tests. Like they might ask you, write the formula of the structure responsible for the peak at 60. So you would say C2H4O2 plus. And that's okay. You can still, that's a good question. You could still lose just one electron, become charged, and not lose any. And that's why that peak exists. Yeah. Okay. Now, for C, the IR spectrum of the unknown compound is provided below. Identify the bonds responsible for the following peaks, okay? 2900, okay? Well, we look at our data here, and I would probably say they would allow 2 answers here, but what would you say the 2900 peak might be? Okay, it could be the OH due to the carboxylic acid, but it also could be the CH bond as well. Okay, the 1700, I think in this case they would accept either. Okay, the 1700 is the C double bond O bond that's present here. Okay. Yeah, you just write the bond out. Yeah, you can write it exactly the way they write it in the data booklet here. Okay. Now, going back to this for a little bit, if you have a formula like C2H4O2 with only one functional group, what are your possible functional groups that you could have in this structure?
You can have a carboxyl group.
You have a carboxylic acid, or what, Marina? Oh, okay. What's the other one? Nope.
Ester.
Okay. Both of those have the C double bond O in them. Okay. You shouldn't ever have an aldehyde or ketone if you have 2 oxygens, because the IB has said that you're only going to have one functional group each structure. So you're not going to have like 2, like an aldehyde and a hydroxyl, or a ketone and a hydroxyl. So you're probably going to have something like this, which is also confirmed by the presence of this in the structure. You've got that C double bond O. Now the OH is up for debate. We're not sure yet. Well, actually, we are kind of sure, because when you look at the structure, you see how broad this is right here? That's definitely an OH peak. Yeah, because that's one of the descriptors on here that says the OH is very broad. So the CH would be very strong, like it goes down deep, but it's actually pretty narrow. Yeah. So this is definitely an OH. Yes. How wide it is, yes. Okay. Now, draw the structure of the unknown compound. Well, if you know it has an OH and you know it has a C double bond O, then by process of elimination, you only have one possible structure you could have. It has to be this, because this is the only structure with 2 carbons that has a carboxylic acid in it. Okay. Okay. Now, with that structure, yes, Matthew. No, it's just ROR. When you write RCOR, it implies a C double bond O. Yeah. That's ketone. Yeah. So deduce the number of signals / peaks and identify the splitting pattern of each signal. Okay. How many signals are there present in this structure? 2, because, well, sorry, the number of signals are 2 because there's 2 environments, right? So this is an environment. Well, the splitting pattern is the neighbors. Okay, so this environment, how many neighboring hydrogens does it have? None. So its splitting pattern is what? 1. It's a singlet. Yeah. And this one also has no neighbors, so it is also a singlet. Okay. So you have 2 singlets here, and the ratio of the peaks, a ratio of the area under the peaks would be what? What would the ratio of the area under the peaks be? 3 to 1. Because the area under the peaks, remember, represents how many hydrogens are each environment. Yeah, the area under the peaks, that's also the integrated trace. That, remember that line that we said we measure next to each peak? Like, there on these NMRs, you're going to see lines like this. where like their lines like, and so when you measure those, that's the equivalent of measuring the ratio between the peaks. Oh, okay. It's okay. Yes.
So the point is you have to explain that because of the changes of the state there. And you can be guessing on these questions.
Well, like, what do you mean?
Like, it would probably say, use the Ionic state
No, they would just say, well, it would say, no, like the questions I've seen on the test were like, state the number of signals and the number of the splitting pattern for each. They would just say that. But you'd get 1 mark for saying the correct splitting pattern for the number of, like, it's like a 1 mark question where you get one, like, total credit only if you identify both splitting patterns correct and the number of signals. Yeah, and each are 2 singlets. That would be the full mark. Yeah, like you said, they don't want you to just guess 2, so they would make it tied to something else so that there's less likelihood that you could just guess it right. Oh, it's 2 signals and they're each singlets. 2 signals. Sorry, signals. Signals being environments or yes. I guess signal is the actual representation of the peak, and that peak represents environments. Singlets. Because there's no neighboring hydrogen, so you add 1 to them. Okay. Yes. Oh, that's how many hydrogens are in each environment. Oh, not in this question you didn't, but I was throwing that question out there. Because I think that was on the, that question was on the mock exam, but I crossed it out because we hadn't done it yet. There was a question like that. So you just come up with the ratio of hydrogens in each environment. Okay. All right. But again, not everything has to be the same structure. It's still organic themed. And so what they might do is on like part F and G, go in a different direction organic. And so what they start talking about now is propan-2-ol, okay? And it says propan-2-ol can undergo oxidation. Okay, identify the product and the reagents needed to produce this product. Okay, so 1, what kind of product are you producing from the oxidation of propan-2-ol?
Ketone?
Let me ask you this, okay, and I'm not saying that you're wrong, but let me ask you this. What happens when you oxidize an alcohol? You take away hydrogens so you can gain an oxygen bond. Okay, so you take away this hydrogen to gain an oxygen bond. Okay, but Cass did ask a good question. What degree alcohol is this? Secondary, because it's bonded to a carbon that has 2 carbons bonded to it. Okay, so that secondary alcohol is going to turn into this structure, which is a what? Ketone. Yes. Correct, because it has no H's to lose. It's a 2-step. Yeah. So reagents, Cr2O72 minus, acid, and heat. Yes, because you need all of that. Now this is your oxidizing agent, but you do need acidified and heat. It needs to be acidified. The solution needs to have acid in it. Oh, yes. It's okay. To 1 carbon. It's still, well, that's a methyl, but you still treat it like a primary. Okay. Now, this is my fault. Sorry. Letter G is a higher level. I didn't bold it, but letter G is higher level. Sorry. So if you're HSL and you're wondering what, I'm not supposed to do this. Yeah, so this is higher level. I forgot to bold it, I guess. And so that is definitely a higher level topic. Yes. Okay, that's a good question. So SN1 is tertiary. SN2 is primary. Secondary, you can do either one. So the IB would actually accept two different mechanisms here to get the same answer. So for a secondary one like this, you could either do SN1 or SN2, whichever one you feel more comfortable with, just do that. So if I'm doing this with this, I could either do this, oh wait, hold on, I'm sorry. Formed from 2-chloropropane. I was doing the product. I was like, that makes no sense where the OH is at. Sorry. So propanol can be formed from nucleophilic substitution of 2-chloropropane. So that's 2-chloropropane. So this looks like this. And then it ends up forming this. And I would draw the wedge dash if I'm doing this SN2. Yeah, it's a transition state. It's carbocation intermediate. Yeah. So it's either this is SN2 because it requires both species in the first step, or you can do it as an SN1. For a secondary, yes, they let you do whichever. And this is SN1. Yes, Matthew. Well, one, if the mechanism is different. Two, the rate law is different. Three, the type of degree of carbon that undergoes it is different. So I don't understand your question. Like, they're completely different. Yeah.
So the CL arrows to indicate that the electrons are moving out of the bond.
Yes, to create a Cl minus ion, correct. You always start at a lone pair or a bond, and you always point at an atom or a bond when you're making a double bond from a single bond or something like that. But yeah, you should always make sure your arrows are going the correct direction and to form bonds. There is more to this. Oh, yes, Cass. The solvent. Yeah. So remember, there is either protic or aprotic solvents. Protic solvents have hydrogen bonding, aprotic ones do not. So what you have to look at is hydrogen bonding is going to interact with what species in these reactions? Like, which species in this reaction is the solvent going to interact with? The OH minus, because the OH minus also has hydrogen bonding. So in one of these reactions, it doesn't matter that the solvent interacts with the OH, which is SN1. So you would have a protic solvent there because the hydrogen bonding would actually help stabilize the carbocation and accelerate the reaction. In SN2, a hydrogen bonding would prevent the OH from attacking the halogenoalkane, which would slow the reaction down. So you want to focus on when you're explaining solvents that the hydrogen bonding that's present or not present would interfere with the nucleophilic substitution. You're welcome.
So is SN1 not interfering?
Yes. It would, because this whole reaction is dependent on OH being attracted to the halogenoalkane, not something else. Okay. Back to here. Back to question number 2. The Haber process is an important industrial process to synthesize ammonia. The equation is given. Okay. Now, A, state the effect on the position of the equilibrium and the equilibrium constant if the temperature is decreased. Okay. So to determine this, what do you need to know about the system? If it's endothermic or exothermic, correct. And because delta H is negative, what is it? Exothermic. So that means the heat is on the product side. Okay. So if you were here yesterday, you saw this kind of analogy. Okay. Now, what happens to this balance if you decrease temperature? Well, you have, it tilts toward the reactants, yeah. So N2 plus 3H2 and then 2NH3, and this is a smaller amount of heat. So it needs to shift which direction? To the right.
Right.
Yes. So you shift to the products. That's the position of the equilibrium, would be shift to the products. Now, because temperature is affecting the reaction but not allowing you to return to the same ratio, because the weight has changed, your equilibrium is different now. And because of that, because you have more products, your K value will do what? Increase, because K is products over reactants. So temperature is the only factor that affects K, because every other factor allows you to return back to the same equilibrium with the same mass on that one side, whereas temperature affects the amount of that mass. And then, so even if you return to equilibrium, your ratio is not the same. Marina? Oh, I thought I saw your hand up. Okay, so that's A. Okay, now B. Calculate the enthalpy of the reaction using data in table 11 of the data booklet. Okay, so you go to the data booklet and you see table 11 is bond enthalpy, bless you. So what that tells you is you've got to map out all your bonds to calculate the delta H of this reaction. And so you have N2 plus 3H2 yields 2NH3. Okay, biggest mistake students make, one is N2. Okay, what does N2 look like?
Triple bond between the ends.
Triple bond between the ends. And a lot of kids will draw a single bond because they forget what N2 looks like. H2 is just a single bond. And the second mistake they make is they look at 2NH3 and go, oh, it has an NH bond, so there's only 2 NH bonds. But it's not 2 NH bonds. How many NH bonds is it actually? 6. That's why I have you draw it out. Because a lot of kids will just look at the coefficient and go, that's how many bonds I have, but it's not. Because it's just an instinct. You're just so used to like, oh, if I have 2H2, that's 2 HH bonds. But then you look at 2 H2Os, and that's 4 OH bonds. But your brain doesn't always process that because you're thinking so quickly. You're just trying to get through the problem. That's why taking an extra second to map and draw these things out will minimize those kind of mistakes. And that's what I always emphasize, because it's so easy to get caught up in those coefficients and go, oh, it's just the coefficients. When you look at the molecule, there's actually more than one of those bonds in each of those molecules. So this is 6 NH bonds, which is very different. And again, if you get one bond counting wrong, then you've lost 2 to 3 marks already on the test, on that question. And it's not worth it just to save yourself a few seconds to do that. Okay, so NN and then 3HH. And if you calculate these in your these values without subtracting or combining together, you get 2 of the 3 marks already. So you look up here, N triple bond is down here, 945. HH is 436. And then NH is 391. Okay, 945, 436, and 391. Okay. So 945, 346. Was it 381? I just lost. 436. Okay, 391. Oops. Okay. 436. Bad with numbers. Okay, 436, 391. Okay. So 945 plus 3 times 436 is 2,253. And 6 times 391 is 2,346. Okay. Now, we have to assign the appropriate signs to these values so we calculate the overall enthalpy of reaction. And so on the reactant side, what are you doing with bonds? What are you doing with bonds on the reactant side? You're breaking them, okay? And breaking bonds requires what change in energy?
Breaking bonds requires the addition of energy.
Add energy in, so it's a positive value. So this side is going to be positive because it's going to be endothermic. And when you make bonds, you release energy. So that's why it's negative here. So this should be 2,253 minus 2,346. And you get negative 93 kilojoules. Okay. Now, it's kind of easy on this question because the IB told you what the sign of delta H was in the original problem, right? They told you it was negative. So all you have to do is make sure these values line up to making a negative number, right? There's only one way to do that. And so I guess you'd make them both negative, and that'd be confusing. But yeah, you end up getting negative 93 kilojoules for the delta H in this problem.
The chances are they didn't tell us that.
Yeah,
The other one was only to know where the
yeah,
delta H is.
exactly. So they might do it in a different order. They might have you A first calculate delta H and then B state, yeah, based off that state.
Is it still error?
I think that would be error code forward. Okay. Now C, this is a higher level. This next section is kind of higher level, 3 parts of the question here. So C says calculate entropy. Now, the calculating entropy is delta S, and we treat it like formation. So we look up the S values for all this. I hope that's actually in the data booklet. I think it is. Wait, is it? Is ammonia not in here? That's awkward. No, but it's not in the delta S. That's awkward. Okay, so you couldn't have done this problem with the data booklet. Sorry. Oh, that's annoying. Okay. Wow, someone left just because I'm kidding. They probably just disconnected. Okay. That's my fault. So they would have to give you this information on the question to be able to do it. So let me just look up this. Entropy of ammonia is 192.77. Let me write these down. So 192.77. And then, now, unlike formation though, elements do have an entropy. Like, unlike enthalpy of formation where we said elements have 0, these actually do have values. So this is 130.68. Okay, 130.68. And then nitrogen, these aren't exactly right, but it's the process that I really care about here. Yeah. Yeah, they'd have to. So negative 191.61. Or it's a positive, sorry. 191.609. Okay. So, like in enthalpy of formation, you do products minus reactants. Okay. So it's 2 times 192.77 minus 191.609 plus 3 times 130.68 gets you negative 198.11 joules per Kelvin. Yes. So you treat it like formation. Yes, Matthew. No, it is the measurement of disorder in the system. Essentially, it's how much energy would it take for you to organize it back into absolute zero. So it's always going to be a positive. The S itself is always going to be a positive value. Delta S can be positive or negative because you're changing the disorder, but S itself should always be a positive value.
But like delta S is proportional to
No. Well, there is a way to solve for using delta H surroundings, but that's not what we're doing. Okay. So let me ask you this. Okay. Does this answer, not quantity value, but sign-wise, does this answer make sense sign-wise? Okay, why? Well, specifically what, Evan? Gaseous. Because gaseous is the most affected by entropy. So one of the ways you can identify the sign of a reaction for delta S is the gas moles. And so if you're going from 4 on the left to 2 on the right, that's a decrease in entropy because there's less disorder, there's less randomness, because there's less gas particles kind of moving about. So this negative S does match what this balanced reaction says because it's going from 4 to 2 gas molecules. That's one of the qualitative ways to identify whether it's a positive or negative delta S. Either way, as long as you say gas, it's fine. Now, we solve for, D. Solve for delta G of the reaction. So delta G is equal to delta H minus T delta S. Sorry, we'll assume it's at 298 just for simplicity's sake here. Yes. Oh, thank you. I did not see that. So we need to divide by 1,000. Yeah, sorry, I was busy answering everyone's questions. I didn't read the whole question. I'm sorry. Okay. Yeah, that's unacceptable. Okay. Negative 0.198 kilojoules. Okay. I'm going to tell you this now. If I were the IB, I probably wouldn't do this in kilojoules because I wouldn't have you doing kilojoules because I'd expect you to make a mistake on the next problem. Because well, no, if I'm the IB, yeah, because a student that, like, if I had left it in joules here, a student goes in here and goes, okay, delta H, they would just plug the numbers in. They would just say, okay, negative 93 kilojoules minus 298 times delta S, and they put, oh, negative 198.11. But that's joules. So you'd have to correct that to 0.198 kilojoules. It's funny that you mentioned that because I was going to not do that and then plug it in and just see if anyone stopped me from doing it without writing the units down, just to prove, like, it was just kind of, no, it's okay. You couldn't read my mind. Thankfully, that's a lot of disappointment to be seeing. Okay. Yes. Okay. So this is negative 87.1 kilojoules for free energy. So is this reaction spontaneous? Yes.
Yes.
Yes, it is spontaneous. Now, is this reaction, and this is kind of a follow-up question, is this reaction always spontaneous? Is it always spontaneous? Why? Sorry, let me rephrase that. At all conditions, is this reaction spontaneous? No. When is it non-spontaneous? High temperatures, because your delta S is working against you as a positive number here. So the larger this value is, the larger this whole positive value is, and eventually you'll get to the point where it's 0 and positive. So you could solve for the temperature. You put that 0 here, and you could solve for when this temperature makes it non-spontaneous. That could be a follow-up question as well. So, yeah, HL chemistry is a lot of math. Yes. Was that, you have a follow-up question, Chloe? I thought you had a question.
Have you seen them ask for, like, at which temperature?
Yeah. Yeah.
If they say at which temperature, do they just say at what condition?
No, they'll say at which temperature does the reaction, like, no longer become spontaneous. Yes. Yeah.
So they'll just let you know.
Yes. Yes. Temperature of the environment. Yeah. Okay. Now, let me add another page here. So, last higher level bit here, calculate the equilibrium constant of the reaction. So delta G is equal to negative RT ln of K. So, oh, did I? Oh, I didn't put the page in the right place. Okay. So, delta G is negative 87.1 is equal to negative 8.31 times 298 times natural log of K. That's a really good question, Cass. It's supposed to be in joules. Why? Because 8.31 is joules per mole Kelvin. Yes.
That's why it says 8.31. That's not right.
Right.
It's not right.
So,
Usually it's like times 10 or
yeah,
whatever.
if you're writing your units down, you're gonna catch that. Okay, it's 8.31 joules per mole Kelvin, which means the other side has to be joules. So it's negative 87,100 joules. That which affects your answer by a factor of 1,000. So it's not any like small mistake there. 80. Yeah, it does. Oh, for the equations, no. But for the constants, they do, and that's enough. 35.17 natural log of K. E to 35.17 is equal to K. And you get a really big number. 1.88 times 10 to the 15. It's very spontaneous, so you shouldn't be surprised at this very big K value, because if you're releasing that much energy as free energy, it's going to be very spontaneous. So K is going to be very big. That's okay. Now, if somehow you got a K that was less than like 1, then you did something wrong. Because a spontaneous reaction always has a K greater than 1. So if you get your answer, you get like 1.8 times 10 to the negative 15, then you did something wrong. Because it has to be greater than 1. Yes, ma'am. No. Yeah, I know, but that's not related to this. That's not related to delta G. Yes, Rachel. Okay. The sign of delta H. Yeah. Well, see, that's the thing though. You have to know that whenever you break bonds, it's positive. You make bonds, it's negative. So it's always the left side is positive, the right side is negative. That's just reaffirming. That information I gave you is just reaffirming that. And so this side should always be positive because you're breaking bonds. This side should be negative because you're making bonds. If you combine together, you should get this every time. Oh, 1.88 times 10 to the 15. No, it does not have units. Okay. Oh, sorry. There's a chat question. Oh, yeah. Grant asked the same question Cass did. Sorry. Okay. So, yeah, write your units out. It's too easy just to write numbers down and assume that they all work out correctly. And chemistry is a lot about making units match. And that's a difference between, like, I mean, when you think about it, I would say there's probably about, for higher level especially, there's probably about 15, 20 marks worth of math throughout the whole test, and units making mistakes here and there. I mean, it's probably enough to lower you a grade boundary by not writing your units out. So if you want to risk it, that's fine by me. Don't say I didn't warn you a million times. Okay. So F, identify the strongest intermolecular force in NH3. Okay, what's the strongest intermolecular force in NH3? Huh? Hydrogen bonding. Are you okay? Okay. G. Okay. What's the electronic geometry for NH3? Which one is it? Which one is it? It's tetrahedral. Because electronic geometry does not factor in lone pairs. It does not treat lone pairs differently. It treats them as a normal bonding pair. So it's tetrahedral for electronic geometry. Trigonal pyramidal is the molecular geometry of the structure. Okay. Yes. Yes, correct. So there are only 5, well, SL there's only 3 possible, HL there's only 5 possible electronic geometries. What's the bond angle between the H and H bond here? 107. Huh? Yes, they're all 107. Yes, correct. A pyramid. An equilateral pyramid. Huh? Tetrahedral is 109, 109.5, 110. Yeah. So I would say if you just remember again, I would memorize the electron geometry angles, and every time you have a lone pair, just take away 3 degrees. That's a safe bet. So trigonal planar starts at 120, goes to 117. Tetrahedral is 110, trigonal pyramidal is 107, bent is 104. That's fine. They give you a little bit of leeway on the angles. Oh, let me get rid of that 110, so looking at later. Okay. Okay, higher level. Explain in terms of atomic structure why NF5 cannot exist, yet AS5 can. So why can NF5 not exist and AS5 can? Okay. That's part of it. So what is happening if N bonds 5 times the fluorine? Yeah, but like what do we call that type of molecule when you have 5? Expanded octet. And for an expanded octet to occur, you need to have the orbitals to allow that bonding to occur. And like Evan said, you need an empty D sublevel. And elements on the second energy level have no D sublevel, which is why nitrogen cannot have an expanded octet, whereas AS arsenic can. Because arsenic's on the third energy level, so therefore it has an empty D. There's no electrons in there, but by default, any element in the third period has a D sublevel that is present. So like the first energy level has S, then S and P, SPD, SPDF, and then all the way down. Yes, you don't start filling those D orbitals until you get into transition metals, but it's still present. So that's a question I've seen them ask before. Understanding for higher level, like what an expanded octet requires. Yes, but you don't fill it until you get to transition metals in the 4th row.
The second one, they don't have it based on the
Yes,
third can technically be like
correct. Yes. Elements on the third period and downward have an empty D sublevel.
They could say like AL.
Yeah, AL would have it. Now, the AL wouldn't usually do it because it doesn't have 5 valence electrons. Usually you need 5 or more valence electrons as well, but it is possible the AL could. Yeah, S could definitely. SF6 is one of the most common expanded octets. Yeah. That's with complex ions and colored compounds and things like that, yeah.
So like Na and Mg have it, but you just
Correct, yeah. Yeah. It's generally non-metals, yeah. Yes, the split D sublevel. Okay. Oh wait, did I mess up these pages? Oh, they're all on this page, that's why. Okay. I didn't realize there was like 3 questions on this page. Okay. I condensed it so like you wouldn't have a bunch of pages you had to print out. Okay. So that's question 2. Okay. So look, question 1 had topic 10, topic 11, a little bit more topic 10. That was mainly that. Topic 2 was letter A was topic 7, B was topic 5, C was 15, D was 15, E was 17, F was 4, G was 4, and then H was I guess 14 on that. So you did 7, 5, and 4 all in the same topic of question. Okay. Now, everyone's favorite, the Winkler method. Okay. Now, things you need to remember about that. Okay. 1 mole of O2 is 4 moles of S2O3 2 minus. And that parts per million is equal to milligrams per decimeter cubed. Okay. So a 500 centimeter cube sample of water was collected, bless you, and tested for dissolved oxygen by the addition of MnSO4 in basic solution, followed by the addition of acidified Ki. It was found that 25.0 centimeters cubed of 0.0500 or molar Na2S2O3 is required to react with the O2 in the 500 centimeter cube sample. Yeah, this is BOD. Okay. Wait, what? I made up these numbers, so you might have gotten negative. We'll see. Okay. So I kind of fudged these numbers, so maybe you did. Okay. Oh yeah, I think it did because that concentration is really high now that I look at it. Okay. So the idea is it's a normal neutralization question. So you have your known and you have your unknown. And you're trying to find the molarity of the unknown, so you need to find out how many moles of O2 are present. So what you have to do is you have to convert your molarity and volume of S2O3. Now they write it as Na2S2O3, but it's just the S2O3 that you care about. The Na is just a spectator ion. And so you can do it either proportion method or the factor label method. 1 decimeter cubed is 0.0500 moles of S2O3. And then 4 moles of S2O3 is 1 mole of O2. And you get 0.003125 moles of O2. Sorry, say that again? Yeah, you would just set it up as a proportion 0.0500 moles per 1 decimeter cubed is equal to X over 0.025 decimeters cubed. And then you'd set that moles of S2O3 to 4 moles of S2O3 to 1 mole of O2 to get the same moles of O2. Yes. You flip the ratio whatever way you need to do it. So the molarity, though, is 0.003125 moles divided by 0.500 decimeters cubed. It's just 0.00625 moles per decimeter cubed. Okay. But it says calculate the dissolved oxygen content in grams per decimeter cubed. So we have to convert this moles, into grams of O2. And I get 0.2 grams. No, that's not right. 0.00625 times 32. No, that is 0.2. Okay. Per decimeter cubed. Okay. Now, well, the decimeters cubed staying the same, so I just didn't write it. So I just converted the moles part. So yeah, oh, I see where this is headed because that's 200, isn't it? Because you need to convert to milligrams to get the BOD. So 1 gram is 1,000 milligrams. So your parts per million is actually 200. That's my fault. Okay. So yeah. That's the molarity. So the question asked me not for molarity, but it asked me for the value in grams per decimeter cubed. So I have to convert my moles to grams of O2 to get grams per decimeter cubed. It just depends on you. Just pay attention to the question. They might just ask you for molarity instead. Wait. Yeah, this is the answer for the part here. Because it asks for the concentration in grams per decimeter cubed. Yes. Yeah. It's about 11 to 12, yes. But you don't need to memorize it, they'll tell you the problem. Now I just realized the problem is now you're gonna get a negative like 189 for your answer because you're supposed to subtract the answer you got here from 11. So that's my mistake. I made a mistake on setting up the problem. Yes, Marina.
You just have to remember that. Are you always multiplying the molarity by 32?
Theoretically, yes. Yes. Yeah. But you just need to remember that that gets you in milligrams because if they have you stop at grams, you got to make sure you undo that part, the 1,000 part, right? So yeah, as long as you remember going from 30, I multiply by 32,000 gets you milligrams per decimeter cubed. You can undo whatever you need to do, but yes, it is multiplied by 32,000 every time. So the problem with my question is I changed the numbers so that doesn't work because when you ask for BOD, you're supposed to do 11 minus this. So you get negative 189 according to my problem, which is bad. So the IB will do better at making up numbers that work for your question. So that's my fault. Yes, correct. You want it in decimeters cubed, yes. Yes.
So what do we do in BOD? Like, wasn't that a question like deduce based on the BOD? I've never been wrong. Oh, like if it's safe or not?
No, like I mean,
Like, what does the BOD mean?
the BOD means how polluted your water is with organic material. So the closer your BOD is to the maximum solubility, the less polluted it is. Generally speaking, if your drinkable water is like a BOD of like 1 to 3, and then anything higher that is starts to become unsafe to drink. Yes, correct. Okay, now this is the SL part as well. MnO2 plus I minus yields Mn2 plus, yes. Oh, Grant, do we need to know why 11? No, that's just given in the problem. Okay. So it says determine the balanced half reactions here. Okay, so you got to split these up into 2 half reactions and then solve for them. Now, technically, you don't need to know which one's oxidation and reduction first. You can just do them and just figure out which one's which. So like just do them both and then figure out which one's which, because one of them is MnO2 yields Mn2 plus, and the other one's I minus yields I2. Okay. So the left one, how do we balance that? What's the first thing we do? Check the coefficients. So the MNs are, what did I just do here? I don't know. That's what I'm sure. What? Okay, that's nice, but I don't want it now. How do I get rid of the ruler? Oh, okay, that works. I just swiped it out. Okay, so you check MNs, they're balanced. Then you add what? H2Os to balance the water. So 2 H2Os, and then you add 4 H+.
Add H plus, and then you balance charges with electrons.
Okay, so it's 4 plus and 2 plus, so you add 2 electrons on the left. So therefore, which half reaction is this? It's the reduction, because you're adding electrons to the reactant side. Okay. Now this one, you have to balance the I's first, and then you just have to add 2 electrons to this side, which is the oxidation. Okay. Now, how do you combine these reactions together? make sure the electrons are the same. So in this case, they are already the same, so they can just cancel out. And for HL, that means N equals 2, by the way. For HL, N equals 2 in this reaction because you're canceling out 2 electrons. So it just ends up being 4H plus MnO2 plus 2I minus yields Mn2 plus I2 plus 2H2O. Yeah, so the overall or the half reaction? I think it's a half reaction. Okay. Yeah, so in the half reaction, the way if you really want to make sure your electrons are right, I look at the oxidation number of what's changing here. So it's Mn that's changing here. Okay? So Mn on this side is plus 2 because it's equal to the charge. On this side, Mn is plus 4 because O is minus 2. So it's going from plus 4 to plus 2. So that's changing 2 electrons. It only happens once, so you should have 2 electrons on this side, which you do. Here, it's 1 minus to 0. So that's losing 1 electron, but twice, so you should have 2 electrons. Oh, yeah. So if you want to check the final one, check first the atoms, make sure they're all balanced. Then you'll notice like, oh wait, I have ions on this side, I don't have ions on this side. And then 2, make sure all your charges add up so they equal each other, not equal to 0, but they equal each other. Yes. I don't think there's any way that you could have that where the atoms and the charges all add up correctly and it not be right. Yes, Matthew. Yeah, that's another way to think about it. That's one of the definitions you can talk about, yes. But yeah, so Matthew does a good point. If you wanted to figure out which one's happening first before you balance, you can look in terms of oxygens, because magnesium is losing oxygens, which is reduction, excuse me, because it's losing the oxygens that would be taking away electrons. And so so that is one way to think about it as well. But the last thing is oxidation state or oxidation number of Mn. Well, there's 1 Mn, 2 Os. And since O is bonded not to a group 1, 2, or 13 or F, it's going to be automatically minus 2. So then Mn is plus 4, write it the correct way. Oxidation state or oxidation number goes last. If you write 4 plus, it's wrong. Okay? So make sure you write it the correct way. Okay. What do we got? About 3 more questions left to go. Okay, let's take an 8-minute break to 10:20, and then we'll do the other half of the test here. I think we're kind of at the right track. The last question is all HL, so SO will be dismissed a little early, unless you want to hang back and ask questions after the test we're going over. But let's take a break until 10:20, and we'll get back. So, question number 4 is a topic 3 and 13 question that addresses period 3 oxides, and that's something that we went over in the topic 3 and 13 video. And knowing that is important for parts of the trends as well. But here, compare the type of bonding found in MgO and SO2. The first thing you want to really identify is the fact that MgO is ionic bonding and SO2 is covalent bonding. Okay, and I would expand on that and define the type ionic bonding versus covalent. So ionic would be the electrostatic attraction between oppositely charged ions. No, that's not the definition. Covalent would be the electrostatic attraction oh man, my handwriting is getting really bad here. Attraction between a shared pair of electrons and positively charged nuclei. Okay, so that's how you describe those two. Now, these reactions with water, you do need to memorize. There's like the Na2O, MgO, P4O10, and SO2 and SO3 that you have to know how they react with water. Metal oxides react with water to form the metal hydroxide, and no hydrogen gas because there's no excess hydrogen. It's all balanced out. SO2 reacts with water to form H2SO3. SO2 and SO3 are easy because you just combine them with the water and that's your final product. So it's H2SO3 and H2SO4 respectively. That you do have to kind of memorize, yes. But if I were to simplify it, I would say, well, metal oxides react with water to make metal hydroxides. That's one generic way to do it. And then the only one that's really tricky, I would say, is the P4O10 one, because it makes H3PO4, and that's not really obvious. So that's the one I would really focus on memorizing, because I feel like if the IB is going to test you on one of them, that's probably the one they're going to test you on. Yeah. Yeah. A lot of people got it wrong. It's okay. A lot. Okay. Now, okay. Explain why the reactivity of group 1 metals increases as the atomic number increases. Okay. So, as you go down group 1, okay. Well, I would establish, what does the reactivity of metals imply? Means losing electrons. Okay, means the ability to lose electrons. So the more reactive metal, the easier it is at losing electrons. What characteristic of an atom identifies how easy it is to lose electrons?
Atomic radius.
Ionization energy. Okay. Well, okay. So here's the thing. I think a lot of y'all were saying different answers for the same idea. Ionization energy tells you how easy it is to lose electron, but characteristics like the number of shells and the number of protons is the trend. But as you go down a group, it's not about the number of protons, it's about the number of energy levels. So the additional energy levels leads to shielding and a decreased attraction. So therefore, the reactivity increases as you go down, because the larger metals have weaker attraction, meaning it is easier to lose electrons. So the lowest group 1 element, francium or cesium, would be the most reactive of all of them. Electronegativity isn't really kind of tied in here, because electronegativity kind of has to do with, with bonding with another element.
Mr. Truong,
Yes.
is the shielding like directly related to the electrons in between the protons and the outer and the valence electrons? Or does it also have to do with
the shielding is the inner electrons. Yeah. Was that your question, Grant?
Yeah, but like, so we wouldn't discuss like it, because whenever you go down the atom or ions become bigger, that it's the distance between the things become longer, so the forces decrease.
You could
Or
say
like
both. You could say shielding or that.
Okay. Like, would they rather one or the other, or does it not?
I don't think there's a preference. No.
Okay.
Okay. Yes. Well, okay. You would make the argument that in nonmetals it's reversed, because what do nonmetals want to do? They want to gain electrons. So what kind of atom would you want that would be really good at gaining electrons? Really small one. So where does reactivity go in group 17? It increases as you go up, fluorine being the most electronegative. Okay. Yes, yeah, least shielding and best nuclear charge. Okay, sketch a graph of the first 5 successive ionization energies of magnesium on the axes provided. Okay, so this one, okay, understanding ionization energy and here, okay. Now, what you need to understand is that ionization energy is going to increase every time you lose an electron, because the protons are pulling more tightly on the remaining electrons. But there is one significant big jump that occurs in every successive ionization energy trend. Where does that big jump happen? Okay, after you lose the last electron in that energy level. So the biggest jump here should be between what? For magnesium, 2 and 3. So yes, you could have this, but you need to have this, and then a steady increase after that.
But there's no values in this.
No, this is correct. This is a sketch. When they say sketch, there's no values associated. But what they're looking for here is the biggest jump dramatically obvious that it's between 2 and 3. That's all they care about. As long as they're A, increasing, and the B, the biggest jump is between 2 and 3, that's all they're looking for. Daphne. Yes. You're starting at Mg, losing its first valence electron, then losing its second, and then so you want to imagine this as Mg, and then this is Mg plus. Wait, what do you mean? Because the definition of first ionization energy is starting at the atom and then losing 1 electron from that. So like, yeah, Mg is 3s2, 1s2, 2s2, 2p6. So then this is Mg2 plus losing an electron. Rajiv.
I have a question on the ionization energy track with the
Oh, I know where you're going with that. That's different. Okay. That is not successive ionization energies of one element. That's comparing the first ionization energy of nitrogen versus oxygen. Because technically oxygen, because it's further right, should have a higher ionization energy, but it actually has a lower one because when you draw out the orbital diagrams, which is why what you should do for every exception, whatever exception they ask you about, draw out the orbital diagrams, because oxygen has 4 electrons in its p, so losing 1 allows it to have a half-filled sublevel, which is more stable. And nitrogen resists that because it already has a half-filled sublevel. So anytime there's an exception in trends, draw out the orbital diagrams, because once you draw that out, yes. Yeah, explain why oxygen's first ionization energy is lower than nitrogen's. No, because those values are listed in the data booklet. Whenever the IB says explain something, Chloe, you're assuming the statement they say is factual. Now, if they say comment on the statement, then it could be true or false. But if they say explain why this is true, you're assuming that the statement that follows is true. Yes. Yes. So, yes, it is recorded. So I will put this on YouTube after the session is over. Okay. Now, for higher level, explain why transition metals form colored complex ions. So this is kind of what Matthew was asking earlier. So a couple of ideas. First, partially filled D sublevel. That's important. Okay, that means you have 1 to 9 electrons in the 3D or the D sublevel. Okay, 2, when ligands bond, they split the D sublevel into 2 slightly different energies. So it goes from this to this. And what happens is that electrons jump up by absorbing visible light. Wait, what? Yes, when they form complex ions, correct. Okay, so what happens is they jump up to this slightly higher D sublevel by absorbing light. And whatever light you don't see, light not absorbed, is reflected or transmitted. And that's what you see, the complementary color. And there's a color wheel in the IB data booklet in case you forget what the complementary colors are. Remember, you don't emit any light, you only transmit the light already. So if you put a complex ion in the dark, there's not going to be any color. It's just going to be dark. It's not like a hydrogen emission where you emit light because of the electricity that you're putting in there. It's absorbing the light that's available and then showing what's not. So like a copper sulfate solution is blue because it's absorbing all the orange color in that. So it's absorbing very small jumps. So again, also, the difference in energy here dictates what color you see. So the wider it is, the higher energy absorbs, the different color you see with respect to that. So the difference in the split, these little affects the color. Matthew.
There's like graphite references that it was like a bar and it would show you the frequency like from
Yeah.
Is that would they show you something like that? I don't know this like this is
No, that would be related to the hydrogen emission spectrum, not this. Yeah.
So we should say all of these things here.
Yes. This is like 3 or 4 more questions. Yes.
You can say that like and the other kind of general and that's not what it is.
Yeah, the complementary color that's not absorbed is the stuff or C. Yeah.
The complementary color that's not absorbed.
The complementary color which is not absorbed is C. The complementary color of the color absorbed is C.
Oh, okay. So it's on.
I was just saying a different way, but it's the same thing. Okay. All right. This one is kind of related, but this is more IMF's topic 4. Okay. The hydrogen halides do not show perfect periodicity. A bar chart of boiling point shows that the boiling point of hydrogen fluoride is much higher than the periodic trend would indicate. Because remember, if we have the same IMFs, it's generally by mass that it increases. Oh, this is kind of repetitive, but it's okay. 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 Na2O and SO3 are 2 oxides of period 3 elements. State the equation for the reaction of sodium metal with water. Okay. And so Na2O, again, metal oxides react with water to form metal hydroxides, and always balance. Anytime they ask for an equation, make sure you balance it. That is. Oh, sorry. Sorry. Na plus H2O makes NaOH plus H2 gas. Sorry, I read that wrong. Sodium metal with water is this. Metals react with water to form the hydroxide and the hydrogen gas. Okay. This is topic 3, reactivity of metals in topic 3. Laura, do you have a question? Okay. Oh, there's a 2 here too. Sorry, 2, 2, 2, 1. Yeah. Okay. Now, this is another one. Describe 2 changes that could be observed during this reaction. Okay. What could you observe in this reaction? Yeah.
The sodium metal, like it becomes like a piece of sodium metal grows smaller, like it becomes
Right.
smaller and smaller.
Yes. So 1, gas is produced. 2, the sodium metal gets smaller and smaller. What else could you measure about this solution?
Heat.
The heat also and pH. So there's a lot of different ways you could measure how fast this reaction is going. So you could measure pH, gas production, temperature, okay, size of the Na metal, all of that. Okay. Temperature would be increased. This would be an exothermic reaction, yes. Predict the relative reaction rates of lithium, sodium, potassium. Well, lithium would be the weakest, slowest one. Look at me. Potassium. Oh, this is almost exactly like 4. Huh? Because in group 1, yeah, it's all the group 1. I didn't realize this question is exactly like the previous question. Sorry, but it was a good review. Yeah, but I did steal, like, no. So I did steal a question because I was running out of time because I wanted to get this out before this weekend. So like I took this question and I thought it was a slightly different question, but it's very repetitive. The first, like these, like the first 3, the last 2 are ones that I kind of wrote. And this one, I guess I just snuck in here somehow and I didn't read what I was trying to accomplish here. Okay. Why is the boiling point of HF much higher than the boiling points of other hydrogen halides? Has hydrogen bonding. Okay. Now, that's not all you have to say to get the credit. So be careful about that. Okay. 1, you need to talk about hydrogen bonding versus dipole-dipole. And you need to say that hydrogen bonding is stronger attraction, which means higher heat needed to boil. So you need to explain why, like, completely. And so comparing that, say, okay, HF has hydrogen bonding, the rest of them have dipole-dipole. But then you have to say, well, hydrogen bonding is a stronger IMF, which means a greater attraction, which then means it takes more energy or heat to cause it to boil. You have to tie all this stuff together, okay? Yeah, Matthew. No. No, not specifically to do that, no. Yes, ma'am.
So what do you have to say to this?
No, you can just say it's stronger. Yeah. What do you mean? Well, you do is you talk about the difference in polarity. And so hydrogen bonding has a much larger polarity difference, which means the attraction with the positive one versus the negative other would be higher. Hydrogen bonding is just a really strong dipole-dipole. That's really what it is. It's just so strong that we assign that. Oh, yeah, sorry. Okay. Why is HF considered hydrogen bonding, but the other? Well, okay, hydrogen bonding only occurs when H is bonded to N, O, or F. Only H, N, O, only bonded to N, O, or F. H bonded to N, O, or F. No. Yeah. Where'd you get that from? Okay, one for me. Okay. So, yeah, not CL, right, Daphne? Okay. Okay. So, explain the trend in boiling points of HCl, HBr, and HL. Okay. Yes, bonding to N, O, or F specifically. It has to do with electronegativity and size. The fact that NO and F are the three smallest highly electronegative elements makes the hydrogen bonding possible. Cl has a higher electronegativity, but it's larger, so it doesn't have the possibility of hydrogen bonding. No, I'm just answering Grant's question here. Sorry, he was kind of doing a follow-up with that. Okay, explain the trend in boiling points of HCl, HBr, and I. It increases because the mass increases. The mass increase creates stronger attraction, which is then what causes the boiling point to increase as we go along, because they're all the same type of intermolecular forces. Kind of the same idea, yes. Yes, that is going down the halogens, yes. Explain why the ionic radius of a chloride ion is greater than the atomic radius of a chlorine atom, okay? Now, anytime you talk about radii of ions or atomic, I want you to identify A, how many protons and how many electrons you have in each one, because I think that's really important to help you differentiate. So protons and electrons. So this has 17, 17, and 18, and 17. So anytime you're comparing ions or atoms, look at the number of electrons and protons, because that will be, one of them will be different, so that allows you to compare. Okay, so chloride, Cl minus, and chlorine have the same number of protons, but chloride has one more electron. Okay, and what does that one electron do to the radius? Increases it. Why? It's repulsion. When you have more electrons, they repel, so they spread out more. So this one is larger than Cl. So this is due to the electron-electron repulsion in the atom. The more electrons you have, but the same number of protons, that means there's going to, the repulsion between them is going to overpower the protons. Okay. Na2O does not conduct electricity in a solid state, but it does when it's molten. Pure SO3 does not conduct electricity in either. Well, the idea is electricity require conductivity. I guess I worded this wrong. Okay. Conductivity requires free moving ions or electrons. And a solid ionic has fixed ions that can't move, so electricity can't pass. But once you melt it, you have the free ions that are moving around. The problem with SO3 is covalent molecules never have free ions. So they would never conduct electricity. Pure water doesn't conduct electricity.
You would also want to specify
Yes. Yeah. Yeah, you would say Na2O is an ionic compound, yes. Yes. To get more detail, the fact that you have a larger atom with greater mass means you have more electrons, which then creates more polarity in the molecule. Because the movement of electrons, the more electrons you have, the more movement of electrons there is, the more polarity that can be caused. So. Just the massive, yeah, because you're having to put more energy to move those masses. Yeah. Okay. State the acid-base natures of Na2O. That's basic. And SO3 is acidic. And then knowing the reactions to support that, Na2O plus water yields NaOH. And then SO3 plus water yields H2SO4, excuse me. Yes, yeah. The acidic and basic, the nature is reacting with water. That's the end of the SL exam part. There's one more question, that's HL. And then we'll do that, and then I'll kind of open it up for some questions for people if you want to stay. So SL, if you have some questions, you can hang around. I don't think the HL will take more than like 15 minutes, 20 minutes, and then for that question, and then I'll kind of answer questions for a little while. Yeah, charged ions. All right. Okay. So this question for HL, okay? This is a topic 14 question. Okay, oh, let me move it down here. You're welcome. See ya. Okay. Topic 14, okay? This is resonance and formal charge and things like that. So this is carbon dioxide, and carbon dioxide can exist in these two possible structures. Now, we all know the actual structure, but that's not the point. What you're trying to show here is, do you understand why? And so calculating formal charge is talking about, well, okay, what is its charge in the molecule when it's sharing electrons? And so the O labeled 1 here, we do valence electrons minus bonds minus lone electrons, not lone pairs, but lone electrons. So for example, this is 6 minus 2 minus 4, which is 0. And this oxygen is also 6 minus 2 minus 4, and that's 0. But over here, this oxygen is 6 minus 3 minus 2, which is plus 1. And this oxygen is 6 minus 1 minus 6, which is minus 1. Okay. So deduce giving a reason the more likely structure, it would be number 1, because the formal charges oh yeah, yes, that's true. You are asking for charge, that's true. So 1 minus. The formal charges are closest to 0. You always want your formal charges as close to 0 as possible. Yeah, sure. My mock exam is either going to look prophetic or it's going to look like Rajiv's predictions and not completely miss everything.
If I see nitration of benzene, I'm just gonna fall on my face and go.
How can you not know nitration of benzene by
I
now?
know, but it's like I've seen it like 5 times. And I'm just saying that it can't be on this. It can't be on
5 times.
It's supposed to be dry.
I know. 5 times, Rajiv. I think some kids in here have seen nitration of benzene like 30 times.
Like every time I'm like, can't possibly get me.
No, it'll be there.
Go here, like, let's find some kids just followed disease and started crying in the middle of the game. What do we do?
You're not to be more specific. I'm not going to assume it's Rajiv. Okay. All right. Last bit. Okay. Absorption of UV light in the ozone layer causes the dissociation of oxygen and ozone. Identify in terms of bonding the molecule that requires a longer wavelength to dissociate. Okay, so here's the thing. Yes, Cass.
I have a question.
Yeah.
About like the last one, because I mean, I would go to like, you said the formal words are closest to 0 and 1, but structure 2 has the same distance with 0.
No. Like being on top of 0 is the closest it can be.
Yeah, I know, but structure 1 of them is 0 and the other is plus.
No, you're reading it wrong. Oh, I did it backwards.
Yeah.
Sorry. I did it across instead of down.
Okay.
My fault. Sorry. I read it wrong. I read the table. Don't look at me that way.
We wrote it wrong, so we wrote it wrong. So we're like, what's wrong with your
The judgment in her face when I make a mistake here. Okay. Okay.
Another way you have 100% shame.
That's true. I'm going to learn from the shame. You're right. Okay. Okay. So here's the thing. Okay, Daphne, let's explain. Okay, so they worded it this way on purpose to test a couple pieces of knowledge. So long wavelength, you have to remember that long wavelength is short frequency or low frequency. Okay. Now, low frequency means low energy because they're directly related. So a longer wavelength means lower energy because of those two relationships there. So which of them will require a lower energy? Ozone. Why are you going after Daphne so hard here?
No, you're wrong.
Oh.
I wrote something on my bio exam and I hope it's not wrong.
Oh. Daphne.
Oh, the green one. Yeah. What this periodic table?
I don't know where I'd put it though, but I mean. Okay. All right. So this test did not have you calculate the enthalpy and stuff like that or the photon, but it was just kind of finding a way to address that without having a really long question. So this is like a 2-mark question. Now the last thing, explain why CO2 is a gas, but SiO2 is a solid room temperature. That has to do with the bonding, right? Because CO2 is a simple covalent molecule with weak LDF forces. Yes.
The question about we would stop the first
Bond order
bond order 1.5.
1.5, which is less than 2. Yes. Okay. Yes, you would say that. That's why it takes less energy to break. Okay. They're directly related, yes. Well, actually, no, they're inversely related. The higher the bond order, the shorter the length. bond order is directly related to strength. That's what you want to think about. Okay. Now, SiO2 is a giant network covalent. So you talk about a simple covalent with LDF forces versus a giant network covalent made up of all covalent bonds. So SiO2 has 4 bonds, 4 single bonds to each oxygen, forming this giant network covalent that is all covalent bonds, which is why it's a solid, versus CO2, which is a simple covalent molecule that's only held together by weak LDF forces, which is why it is a gas, because it has a very, very low boiling point. So what? Yes. By default, every molecule has some LDFs. Yeah. And really, when we say mass increases, that's what's really increasing. It's not really the dipole-dipole. Dipole-dipole is about the same. It's the LDFs are increasing as you get more and more mass. Okay. Yes. Correct. Yeah. The only major thing that, well, actually, there's 2 major things that I didn't put on this test, just because I didn't know how long I wanted to make it. But with my luck, those are things on the test. So pH curves and buffers, and calculating like electrolytic cells, like cell potential and stuff like that. But that was on the mock exam as well, so I think it's less like you've at least seen it and talked about it. Like cell potential and stuff like that. But again, I don't want you to bet on this, but if you're at the point where you're trying to like be most efficient or most effective in what you have, let's say I think all of y'all are fairly well studied, but for those of the people that are not very well studied and you're trying to focus on stuff, the rumor is that they've emphasized more of the 12th grade stuff than the 11th grade stuff in a lot of the sciences. And so the 12th grade stuff would be topic 7, 8, 9, 10, 11, which is equilibrium all the way to organic chemistry and analytical chemistry. So if you're trying to prioritize studying, I still think 4, 5, 8, and 10 are the big priorities, but if you're trying to spend a little bit more time on stuff, then organic and like 8, 9, and 10 are really big ones. Okay. All right. So that's the end of the review for the mock exam.